In this video, we will understand how the CPU, which is the brain of the computer, is shared among different processes running in the system. CPU scheduling is essential because it helps us achieve high performance, fairness, and efficient use of system resources. This topic is especially important in operating system because without proper CPU scheduling, systems would either be underutilized or inefficient, leading to slow and unresponsive computers. Hi, Hi everyone, myself Manas Rajani from CS3 and I am presenting this video on the topic CPU scheduling, preemptive versus non-preemptive CPU scheduling. Let's begin. First topic is CPU scheduling. In CPU scheduling is managing processor resources. Now let's understand the role of CPU scheduling in managing processor resources. First, operating system core. CPU scheduling is a critical part of any modern operating system. It decides which process will use the CPU at a given moment. Without a scheduler, processes would compete for the CPU randomly, and this could cause chaos, with some processes starving while others hog all the resources. Second, process distribution. The scheduler controls how different processes take turn using the processor. Think of it as the traffic controller at an intersection, making sure everything flows smoothly and fairly. Third, performance impact. The choice of scheduling strategy has a direct impact on performance. A good scheduler improves system responsiveness, ensures that critical tasks are handled quickly, and helps make sure user gets a smooth experience when reacting with the system. In summary, CPU scheduling is what ensures that multiple tasks can run efficiently without conflicts or delays. Now, what is CPU scheduling? Now let's break down what CPU scheduling actually means. First, a step in CPU scheduling is process selection. First, the operating system has a ready queue. This is where processes wait for their turn to get the CPU. The scheduler's job is to pick one of these processes based on the scheduling algorithm being used. Second, CPU allocation. Once a process is selected, the CPU is allocated to it. This means that process gets to run its instruction on the processor. Third, optimization goal. The ultimate goal of CPU scheduling is to balance multiple objectives. We want to maximize CPU usage, minimize delays, and ensure fair access. The scheduler tries to make sure that resources are used as efficiently as possible while keeping the system responsiveness to the user's need. Now, why CPU scheduling matters? You might wonder, why is CPU scheduling so important? Here's why. First, first of all, maximize CPU utilization. We want to keep the CPU busy most of the time. In large server farms, we target about 90% utilization so that hardware investments are justified and nothing is wasted. And we maximize and if we maximize CPU utilization, the CPU is uh, is being used more than 90% of time and is not being able to sit idle, which is a good thing. We don't want a CPU to be idle and do nothing. We want the maximum result from a CPU that we can get. Second, maximize throughput. The goal is to complete as many processes as possible per unit time. For example, on a web server, this means handling as many requests as possible per second. Third, minimize turnaround time. This is the time from submitting a process to getting its result. Lower turnaround time means faster output, which is crucially for many applications like data processing or complication. Fourth, minimize waiting time. Processes shouldn't be stuck waiting unnecessarily in the ready queue. Reducing waiting time helps improve fairness among processes. Fifth, minimize response time for interactive applications. Response time is critical. Users accept, expect a quick reaction to their inputs, usually within milliseconds, especially in user interfaces or gaming. Now, balancing these objectives is what makes CPU scheduling both challenging and interesting. Now, let's move on to types of CPU scheduling. Let's look at the types of CPU scheduling. The main distinction is between non-preemptive and preemptive scheduling. First, non-preemptive scheduling. Here, once sub-process starts running on the CPU, it keeps running until it either finishes or voluntarily gives up the process. For example, if it waits for input or performs input-output operations. Here, the process can not leave in the middle without completing. The process should be completed so that the next process gets its turn and gets the CPU. Now, preemptive. In this model, the CPU can be taken away from process if necessary. For example, if a higher priority process arrives, this, this allows more flexibility but comes with additional complexities. Now, it's our decision what we have to choose. Thus, we have to interrupt the CPU or we don't want to. Now, let's move on to non-preemptive scheduling. Let's look at non-preemptive scheduling in more detail. First of all, definition. In non-preemptive scheduling, the process keeps the CPU until it either finishes its job or performs an input-output operation. Characteristics simple to implement with low overhead. The advantages the characteristic the main advantage is simplicity. It's easy to implement and there's very little overhead because context switches only happens at predictable points. Now let's talk about the disadvantages. Can lead to long waiting time for short processes like the Conway effect. The downside of non-preemptive scheduling is that short processes can get stuck waiting behind longer processes, causing what we call the Conway effect, like cars stuck behind a slow-moving truck on a single lane road. Now, now let's talk about its few examples. First of all is CFS, that is first come first served. Simple but can cause high waiting times if a long job is at the front. Second, SJR, shortest job first, reduce average waiting time but requires us to estimate how long each job will take, which isn't always possible. This is a perfect picture for this example. One everyone is in a queue, and if this person gets ahead, then the other process will get ahead. Similarly, if this process is gets the CPU and gets completed, then this process will get the CPU and will be completed. No two process can interact with uh, interrupt each other. Now, let's move on to preemptive scheduling. Now, let's talk about preemptive scheduling. First of all, definition. In this approach, the operating system can interrupt a running process and assign the CPU to another process, usually a higher priority or more urgent one. Characteristics better responsiveness handles critical tasks quickly. This leads to better responsiveness, especially for time sensitive tasks. Critical processes can be handled without waiting for a long process to finish. Now, let's talk about the disadvantage of preemptive scheduling. The main cost is overhead. Every time the CPU switches, from one process to another, called the context switch, sometimes lost. Typically, this is 5 to 10 microseconds but can add up if switches happen too often. Examples: round logging. Each process gets a small time slice, say 20 to 100 milliseconds, after which the next process gets its turn. This is common in time sharing systems. Second example, SJF, shortest remaining time first, SRTF. This is preemptive version of SJF. It provides optimal average waiting time but requires knowing the remaining processing time for each job. Preemptive scheduling is powerful for modern systems, especially where responsiveness is key, but it must be managed carefully to avoid too much switching overhead. Now let's talk about preemptive versus non-preemptive scheduling, a comparison. In responsiveness, preemptive can be fast and non-preemptive can be slow because if the current process gets completed, then the next process will get chance to use the CPU. Or talking about overhead, high context switch overhead, minimal overhead. Fairness, generally better fairness, can cause starvation because if a long time taking job came at front, it can cause starvation. Implementation. Implement preemptive scheduling implementation is complex due to time interrupts, and in non-preemptive, the implementation is simple. Use cases: preemptive CPU scheduling is used in real-time OS, multi-user OS, and etc. And non-preemptive scheduling is used in batch processing, OS, and etc. Now let's let's talk about the conclusion. In conclusion, CPU scheduling is central to operating system performance. The choice between preemptive and non-preemptive scheduling affects not only how efficiently the processor is used, but how fair and responsive the system is. By understanding different scheduling strategies, we can design systems that perform better and provide a smoother experience for users. First one, fundamental. CPU scheduling is fundamental to OS performance. Goal-oriented dependent choice depends on system goals. Modern OS preemptive scheduling dominates modern general-purpose OS. Crucial. Understanding trade-offs is crucial for systems. Thank you for listening, and I'm happy to answer any questions if you have. Thank you.